to centralize the alignment marks in the field of view. Likewise, we have infrared illumination there. We see the shadow, it's a lot fuzzier, but you can see. And this is wholly necessary for silicon to silicon bonding, because you can't obviously see through silicon with visible light. We've got level control there, so we want to control it where we have good contrast but without saturating the picture. We have some toolbars here, so we can say draw a square around an alignment mark around the crosshair. So when we have the lower wafer, the pattern that's on that wafer from my demonstration wafers is 4 little squares that are going to sit in the corners of this square. So if I draw that square around, I can align my 4 little squares with the edges of that big square that I've drawn. And then when they line up, I know I've got good alignment. So they're just little tools for helping you to do the alignment. Magnifying glass to zoom in. Shift click, zooms back out again. Then there's an identical toolbar here for controlling the right hand side camera. So there's independent control for any drawings, any doodles on the left and the right camera. We can also save images to disk. So it'll give us a dialog. You can select a save location, give it a file name. The software will then append your file name with dash left and dash right for the left and right pictures. Down here, we have the current positions of the X, Y, theta and Z motors. So at the moment, we're in the home position, which is with the platens centralized. Well, the lower platen is centralized within the chamber. So it's reading 0, 0, 0. And then the Z here, this is telling us the separation of the wafers. So that separation is the same as this separation here. But it just tells us on this screen as well, because it's useful to be able to see it without having to keep going back and forth between the two screens. So on the right hand side column there, we've got the home positions, which is set to 0, 0, 0. These green indicators, they indicate any fault state with any of the motors. So at the moment, there's no faults, everything's good. If the motor hits resistance or crashes or it loses communication or something happens, that will flick to being red. If it's a minor problem, you can just reset the error code there. So say you've moved to the end of the travel in one direction and it's crashed, it will throw an error code. You can reset the error code and then try and move it away. If it's crashed badly and it's got stuck, you'll reset, try and move it away, it will throw an error again. If it keeps happening again and again, you have to stop and then try and investigate what's gone wrong. So the most common cause will be the motor crashing into the edge of the manipulator crashing at the end of its physical travel. There are software limits to prevent that from happening, but it is possible to fool them. Obviously best if you don't fool them, but it is possible. So at the moment, there's a button here to set the position as home. I've centralized the lower platen and I've hit that button, and that's set my home position. If I were to offset the manipulator and then set that as the home position, the software limit would then allow me to keep driving further, and then you have the potential to be able to crash the manipulator. So it is possible to fool the software limit by doing that. Please don't. So it's there to try and protect the machine. So what I would recommend is after you've finished a bonding run, home the stages. So all that does, anywhere, if the platen is offset in any way, it will move it back to the central position, then shut the machine down. Another slight limitation with the system is that in the event of a power loss, it will not remember the position of the motors. So if you've offset the manipulator and then you turn the machine off, when you then start the machine up again, it will think that the position it's currently in is the home position. It can't remember that it's been offset. So that's why I recommend sending the stages to the home position before shutting down. It's fairly important.
Any reason this happens?
Yeah.
How can we reset the...
Okay, so if, say, you've crashed the Y motor, there are two physical ways in which it can crash. Either the manipulator has crashed, there's a hole in the bottom of the chamber that the thing is fed through. If that's crashed and got stuck, or the lead screw assembly on this motor. So you can see here, if you look underneath, there's a little screw. So the motor here drives a pulley on a sort of belt drive, which turns that screw, which then moves the shuttle backwards and forwards to move the manipulator. If this lead screw, if that's hit the end of its travel, or the manipulator's hit the end, you can undo this cover, use a pair of pliers, just to sort of wind the motor away from the physical limit. That will then free it off, and then you can start driving it again. You can reset the error code and start driving it again. Another problem that might happen is if there's some break in the wiring, if this degrades, or I don't know, it's unlikely to happen, but if there's some break in that wiring, if you cut it by mistake or something like that, you'll see an error code because it can't communicate fully with the motor. There's two cables. There's a coloured ribbon cable that delivers power and like position control, and then the grey ribbon cable is for the encoder. So that's how the motor controllers know the position of the motor. That's how they monitor it.
How do you make sure that the platen is the correct position in the center?
We have a tool for that, which hopefully I've got here somewhere. If not, it's in a box outside. No, it appears to be in a box. Anyway, there's a tool that you can secure to the upper platen. It's a little plastic bar with a couple of holes in it. So you can move the cameras around to use those holes to centralize the cameras. And then there are two little metal plugs with a punch in the middle of it. They sit in the holes in the lower platen, and you can then view the cameras through the holes in the plastic bar, move the lower platen around until you can focus the punches in the metal plugs with the holes, so you can align them. Then you know that the platen is centralized. I will demonstrate the use of that tool when Kyle's found it and later on. We can see the platen temperatures and the chamber pressure. Here we can see any force that's being applied. At the moment, the X and Y motors are within the specified software limits. So if you run, I believe the software limits will allow you to move it 7.5 millimeters in either direction. So 15 millimeters of total travel, 7.5 either side of the center point. At the moment, we're within those limits. If you reach the edge, the software will cut in, stop the motors running, and the idea is that it stops before any physical limit is reached. But like I say, it is possible to trick that. If you move it all the way to the right, say set that as the home position, move it all the way to the right again, you can keep tricking it. But best not to do that because you can get it in a muddle. The software will tell you if the wafers are, if it thinks the wafers are in contact. It determines that by if there's a force of more than 20 or 40 newtons or something, it will tell you that the wafers are in contact. If the software believes the wafers are in contact, it won't allow you to move the manipulator because there's no point trying to move the wafer once it's touched. Okay, so the camera controls I've already talked you through. Keyboard controls. So I mentioned earlier the controlling the motors using the arrow keys and the space bar. You've got two different parameters for controlling the XYZ motors. You can either run them in step mode, so If you hold the space bar and just give it one push, it will move by a step of whatever is input here. So currently it's moved it by 100 microns. You can see commensurately the position of the X motor has moved to 100 microns. So if I move it the other way, it will move back to 0.
What's the minimum step you can do?
Sorry?
Is there like a minimum step you can...
1 micron. But you may not be able to see 1 micron of motion because each pixel is 1.16 microns. So you may need to move it 2 micron step before you actually see any movement.
Does it mean that 1.16 is the accuracy of the alignment?
In theory, yes. Yeah. With infrared alignment, I think we specify that it's 5 microns accuracy because the picture is a bit hazy, it's a bit fuzzy, it's difficult to get the alignment spot on. But in theory, we can align to about 1 micron, 1.16 microns technically. But in practice, we can just about manage 1 micron.
Does it depend on the thickness of the wafers?
No, not so much. It does depend on the accuracy of the alignment marks, on how well matched they are between the upper and the lower wafer. So it's very important that they are positioned precisely. So if there's a separation of 67,000 microns on one wafer and 67,005 microns on the other wafer, you're never going to be able to line it up quite accurately. So dependent on the quality of the printing or the etching or whatever of the alignment marks, we can achieve 1 to 2 microns is definitely achievable. Then if we push and hold the motor, rather than running with a step, it runs at a speed, and the speed is specified there. So we have a maximum of 1,000 microns per second. Minimum, I guess, is probably 1 micron per second, but that would be tediously slow. So that's if the alignment marks are not in the field of view when you start and you need to sort of do a spiral search, you'd be holding the button down rather than doing it in 1 micron steps all the time. So it will use that parameter to control the speed, and it will use this parameter to control step sizes if you do 1 push at a time. Theta similarly, the step size is obviously not in microns per second, it's in degrees per second for theta. So you can set the step there and the speed in degrees per second there. So theta has a resolution, you can move it by 0.01 of a degree. So 1 arc second. Bear in mind also that the motors all have some intrinsic backlash in them. So if you set a step of 1 micron, you may have to make 5 or 6 steps to take up that backlash before you actually observe any movement. Home stages, that just sends the motors, if they're offset in some way, it will just send them back to the central position. Set position is home. This is when we use the centralizing tool that I was talking about earlier. When we've got it lined up in the right place, we can set the position as home using that button. Yeah. Then if for any reason you've accidentally put in a step of 5,000 here instead of 500, and you've done 1 step and the motor's like moving, you want to stop it, you can halt it using stop motors. Proceed sends you back to the main screen. So that's pretty much everything that you're going to need to be able to control the system. Here you can view the startup process parameters that you put in. So if you hit start and you think maybe you made a mistake, you can check here. Then you can abort the run, go back, correct the mistake before you do the whole process and realise that you've got a massive log file, or it's saved with the wrong name or something like that, or you put the wrong wafer thicknesses in. View I/O channels. This is basically a diagnostic screen for us. So this shows the input and output voltages and the relay state of all the modules on the PLC controller. So it's pretty much used by us for diagnostics and for doing setup and calibration work. you won't really need to use it. Set pump parameters. This is just an excerpt from what you get in the first screen, the process parameter screen. You won't need to change it, save to say that it's done an oil change. So after 2 years, you replace the oil. You can confirm the oil change there. It'll reset these counters back to 0. It'll ask you for a password, and that will be AML. Then when you've finished your bond, stop process, end the current run and set the system down. Okay. Then you'll get this finish screen. So from here, it shows you the current chamber pressure, the upper and lower platen temperatures. These will be highlighted red if they're hot still. So it's just basically as a warning, remind you that they're hot, so be careful. It will not allow you to open the lid until the temperature is below 200 degrees. That's partly for your safety and partly for to prevent oxidation of the internal components. So if there's oxygen in the chamber above 200 degrees, you risk oxidizing things inside, which can make wire connections brittle and just cause other problems generally. If you forgot to vent the chamber before you shut the run down, you've got an option, last minute option to vent there. You can also view the event log and view the data log using these 2 buttons. Then you can either repeat the run or finish. I forgot to talk through one thing, so I'm going to repeat that run. Okay, start it. I forgot to talk you through this. So this screen will show you which of the lid interlock conditions have or have not been met. So that's located just here, powered lid. Currently it's disabled, so the software will not allow us to try and open the lid now. Won't allow us to do anything. The reason for that is that the lid bolts are not out. So it won't allow us to try and open the lid while the bolts are in, because doing so would just grind the motor. Similarly,
Touch something outside the bolts.
sorry?
The bolts need to touch some sensor or something.
Yeah, there's some micro switches on the bottom. There are 2 micro switches, one normally open that tells the software that the bolts are in, one normally closed that tells the software when the bolt's out. So it knows when they're either all in or all out. So if I only take one out, it knows that some are still in. When I've got them all out, that will turn green. There we go. Now all the conditions have been met. So the other conditions are the platen height. I mentioned this earlier when I was talking through the configuration program. It insists that the wafers are separated by, sorry, not the wafers, the platens are separated by at least 2 millimeters. That's to prevent such that when you try and close the lid again, to prevent them from crashing. It shows you the current height, or the current position of the platen, and that's the limit value there, so it has to be below that. Upper platen and lower platen below temperatures. The limit is set to 200 degrees. Currently they're both below that, so it's fine. If they were at 300, obviously these would be red until it had cooled down enough. Lid bolts out and the system vented. So if the system is under vacuum, it will also not allow you to try and open the lid because the lid's being sucked down by the vacuum. And again, that will grind the motor if you try to open it. The way that the system knows whether it's been vented or not, it judges that by whether or not the exhaust valve has opened. It does not judge it by what the actual pressure is. So when you first come in the morning, you'll switch the machine on, it will be vented, it will be at atmospheric pressure, and it won't allow you to open the lid. And you'll think, why not? It's vented. The reason is because the exhaust valve hasn't opened, so you just need to toggle the exhaust valve on and off, and then it will meet that condition. It's slightly annoying. I don't know why it does that. But yeah, that's important to remember. It judges that the system is vented by whether or not the exhaust valve is opened. Okay, so that's manual mode dealt with. Automatic mode. Sorry. We can select anodic bonding, direct bonding, or an other mode. Okay. Other bonding might be thermocompression, metal to metal, eutectic, glass freight, solder bonding. These are all kind of methods. I think to start with you'll be using anodic bonding. So which systems are made available to the automatic mode depends on which one of these you select to start with. So in anodic mode, the high voltage bonding voltage will be available. In direct mode, it will not. And other things like that. When you select direct bonding mode, you then get two further options for a pin chucker or standard platen. This is for some ancient mechanism that we had to try and do center out bonding. It's a horrible over-engineered device. We now have this simple pin to accomplish the same thing. So nowadays, all machines are going to be fitted with a standard platen. This pin chuck is no longer relevant. We've got the other mode there finally. So I'm just going to go into anodic for demonstration purposes. We get a similar screen to start with. You can put the run name in. Test say. Similar button to generate the log file names. Same parameters to control the frequency of the logging. Then the only thing that's different is we have here the recipe function. So any recipes that you've created and saved will be stored in a folder on the C drive, and they'll be available for you to select here. So we've equipped the machine with a default anodic bonding recipe, which is anodic default, and then live test, which should be life test. That's what we use for stress testing the machine in the factory. So we just run simple tests, simple sequence of steps, run it again and again and again. So